Welcome to the video on mass spectrometry. Mass spectrometry is a technique that we can use to explore the structure of organic molecules. What happens is we take any given organic molecule and we hit it with a high energy electron beam. The electron beam kicks out one electron, leaving us with the molecular ion, which ends up being a radical cation. So it's positively charged, which becomes important in just a second, and it's a radical because we've removed a single electron. So an electron is ejected, forming the molecular ion, and we call that M+. Mass spectrometer, this is the instrument. So we have our sample here, and then we hit it with the electron beam, and we end up getting our radical cations here. Now, the neutral fragments, because they're not charged, are unaffected by the magnets, so they end up being sucked out to the vacuum pump. So the only thing that we see in mass spectrometry is the positively charged ions. And so because the magnets, they are pulled through the magnet and they hit the detector down here. And so then we can look at the mass to charge of the fragments that hit the detector. And so we really need to remember that only the positively charged species reach the recorder. Here's a typical mass spectrum of pentane. Remember, pentane has 5 carbons and it's completely saturated. Now, the M+ peak, which would be the molecular weight, is 72. So the M+, or the molecular ion peak, is 72. Let's talk about the MZ. So we're talking about the x-axis units. And M is mass and Z is charge. So it's the mass to charge ratio. So down in this area of the spectra, we're definitely talking about a single charge. So then we're talking about the full mass per the single charge. And so this is the molecular weight of the molecule that we're looking at, 72. Mass spec can easily detect the molecular ion, so it can easily tell you the molecular weight of the compound that it's looking at. However, the other thing that mass spec does is, because of that electron beam, it also can break the weakest bond. So we have situations where we're actually breaking a bond, and then pieces of the molecule fall off. For example, if we lose 15, so if we have the molecular ion minus 15, that would be a methyl group, this Z-like cut in our molecule. So if we draw where the cleavage happens, where the break happens in the molecule, it'd be like that. So this piece right here would be 15, right? And then this piece right here would be 57, because 72 minus 15 is 57. Obviously, they both have to add up to be 72. This piece, if positively charged, would be detected at a 57. This piece, if positively charged, would be detected at a 15. Now, if we take the cut here, what we have instead of 15 is this mass would in fact be 29, right? So it's 12 plus 3 plus 12 plus 2, 29. And then the bottom piece, the bottom down here, this piece, this 3-carbon piece, would have a molecular weight or a molar mass of 43. So here's the peak right there, okay? And that peak is going to be the molecular ion minus 29, because this piece broke off, and then that piece is what is shown in the detector. And then you can keep going, right? And so this one here, this would be 43, and this would be 29. And so you can see that the other two pieces, right, it breaks evenly. And so then we get 42 and 29 again. And so I hope you can kind of see how this works. So the mass to charge is the ratio, and because our charge is equal to +1, the M in this case is in fact the molar mass. And I hope you can see too how we determine where the molecule fragments. So the molecular ion is the full molecule with only a positive charge of 1 electron missing. and that would be 72. And we call that the molecular ion. So we have 5 carbons, and if the molecule breaks here, we end up with a 15. If the molecule breaks here, we end up with a 29. If the molecule breaks here, then we end up with a 43. And if the molecule breaks here, then we end up with a 57. So the more stable the fragments, the more abundant they will be. If we go back for a second to the slide with the spectra, this peak right here is the most abundant. It shows the abundance of 100%. And that is actually called the base peak. And the base peak is the peak that represents the most stable fragment of the molecule. So there's really 2 things that we have to know about mass spec. We have to know the molecular ion, which is the molecular weight of the total molecule before any fragmentation happens. We've just simply gotten rid of an electron. And we have to be familiar with the base peak. And the base peak is the largest peak in the spectra, and that's because it represents the most stable fragment, which also has the greatest abundance. Now, we said that we have carbocations and radicals. We have a situation where we have a 43 molecular weight mass to charge ratio. Here's what the species can look like. We know that primary carbocations aren't so stable. It turns out that if we lose hydrogen, so we lose 2 hydrogens, we form a double bond and we end up with a carbocation, which is much more stable. This additional species is present in the spectra as well. So we see the main peak maybe being 43 with a little shoulder peak or a little side peak being 41, indicating that it's just another species related to the 43 peak. So the more stable fragments are more abundant. So here is a perfect example. So this is just a constitutional isomer of the one we just looked at. In this situation though, we can break one bond and we can form a secondary carbocation. And so you can see that we have the molar mass, the molecular ion, is still 72. And if we break off that methyl group there, we end up with a secondary carbocation. And so that you can see that this species right here is much more abundant than the 57 peak in the normal pentane that we looked at just a second ago. And then for the 43 peak, you can imagine breaking this bond right here, breaking off an ethyl group, giving us a secondary carbocation as well. And so you can see through the fragmentation pattern that it's possible to determine the constitutional isomers from one another because of the way the fragments break, because the original molecule breaking certain bonds gives us a more stable carbocation, giving us a more abundant fragment. So the peak at mass to charge 57 is more abundant in this molecule than it was for normal pentane because of the secondary carbocation, and that's going to be more stable than the primary would have been for pentane. So secondary carbocations are more stable. Now, in order to do mass spec properly, we really have to talk about isotope because mass spectra instruments are very precise and they give us very detailed molecular weight information or mass information. And so the incorporation of an isotope in the molecule is definitely going to affect the spectra. And for carbon, for example, 1% of the carbons that are in naturally occurring compounds is carbon-13. And so whenever we see a peak, we're going to see a little tiny M+1 peak, indicating that the additional neutron mass from the isotope. Now with hydrogen, it's very, very, very small of a percentage, so we don't necessarily see that in hydrogen, although somebody who does mass spectrometry for a living uses this natural abundance of hydrogen, deuterium, in their calculations. Nitrogen, oxygen, sulfur, and then we really, really gain a lot of information from these two here, chlorine and bromine. And that's mainly because the chlorine and the bromine become M+2 peak. And so that's That's going to be something that's very characteristic of molecules that contain bromine and chlorine. Whereas these up here, we mainly think about M+1. So the better your instrument, the more higher resolution you get, and the better capability you have of distinguishing molar masses. Some of the very good mass spectrometers can differentiate between all of these compounds, even though at quick glance they all have a mass of 122. And it's these decimal point positions using the isotope and the natural abundances that differentiate them. For example, C9H14 is 122.1096, and that's because the hydrogen at this natural abundance here has been calculated. So a very high resolution mass spectrometer can really break things down to a very, very detailed mass. This table indicates the exact masses of isotopes, so it takes into consideration the percentage of the isotopes that are out there, and that helps mass spectra be interpreted. So the carbon-bromine bond breaks heterolytically. If you recall, that means that both electrons go with the bromine. And so we can see that. So we're going to be using the arrow that has the double-headed arrow. So if we have one bromopropane here, there's examples where there's a bromine that has mass of 79, and there's examples where the bromine has 81. Because of the M+2, we end up seeing equal abundance of both the M and the M+2 because of the natural abundance. This is for bromine only. Chlorine is different. And then we break that bond to bromine. So we end up with 43, and that's going to be our base peak. And then we have 79 and 81. Because the positive charge is not likely to end up on the bromines, we just see very small little peaks there. So our molecular ions in this case are 122 and 124 right here. So that's the M and the M+2. So when you see something like this, for the M and the M+2, that really indicates bromine. Could indicate chlorine too, and we'll see what that one looks like in just a second. The carbon-chlorine bond also breaks heterolytically so that both electrons go with the chlorine. The carbon-carbon bonds, however, break homolytically. And we haven't learned about this yet. That means if of the two electrons in the bond, one electron goes with carbon, the other electron goes with the other carbon. And that's typically drawn with fishhook arrows. So if you have two chloropropane, the chlorine breaks off very easily, and we just have both electrons go on to the chlorine, both in the case of the 35 molecular weight chlorine and 37, giving us mass charge 43, secondary carbocation, Cl35, Cl37. However, when we break off the carbon, what happens is one of the electrons goes on the carbon here, and one electron goes on the carbon here. And so then we end up with a radical, which isn't shown here. I think it's shown on the next one. Okay, so there's electrons over here, and there's a single electron here. It turns out that this electron hops in and this electron hops in, so that we end up getting a double bonded chlorine, and so we end up seeing a peak at 63 for the 30 molecular weight carbon. And then for the 37 molecular weight chlorine, we have 65. And so this gives us some insight into what we're going to see in the actual spectra. And so the spectra is here. Because chlorine and the M+2 chlorine, so this is 35 and 37. So this is the chlorine with 35, and this is the chlorine with 37. Because the natural abundance is more like 3 to 1, you're not going to see equal ones. With bromine, you saw equal, but with chlorine, on the molecular ion, you're going to see M and M+2. That's the same as bromine. But the abundance of the M+2 is about a third that of the M. So the species here was 63 and 65. Because of the relative amounts of 63 and 65, we know the chlorine is still on the molecule. And if we look, 80 minus 65, that's 15. So this right here is loss of 15. And so we know that we've lost a methyl group there. Now at the 43 point, we don't see the M+2. And so at the 43, we know we've lost our chlorine. And that is, in fact, losing the chlorine. So we have the base peak, which is nice and abundant, which means that it's a nice stable carbocation, which would be the secondary carbocation right here. So we lose the 35 or the 37, and what we have left is 43, and that's the nice stable base peak carbocation. So I hope this is starting to make sense. It's definitely different, so you got to practice. So alpha cleavage. When we talk about alpha cleavage, we talk about breaking off. So if here is your functional group, then we talk about cleavage after the alpha position. So we're talking about this specific bond right here, and that's alpha cleavage. So when we have alpha cleavage happen in alkyl chlorides, but we don't get that so much in alkyl bromides, and that's because of the bond strength. A carbon-bromine bond is 71 kilocalories per mole, whereas a carbon-chlorine bond, so that's most likely going to break. We're not going to be competing with the alpha carbon next to this. Whereas the energies of the carbon-Cl bond and the carbon-carbon bond are very similar. And so you're going to see both happening in a chlorine molecule. And then you look here that the carbon-hydrogen bond, much, much higher energy. So we don't see that as often. So the carbon-carbon bonds and the carbon-chlorine bonds have similar strengths. And so we're going to see both the chlorine break off and the alpha cleavage in those molecules. Whereas the carbon-carbon bond is much stronger than the carbon-bromine bond, making it less likely to fragment or cleave in mass spec. Carbon-oxygen bond also breaks heterolytically, so that just means that both electrons go in the same direction. And so we see here that we can break the bond here or the bond here. So the molecular ion is here at 116. That's mass of the whole thing. If we break it here, that gives us these two fragments. We have a mass charge of 57, which is located here. And then the positive charge stayed here. Remember, the electrons went with the oxygen. And if we break it here, then we get this species right here. So we have a mass charge of 43, which is here. And then this is what's left, but that doesn't have a positive charge, so we don't see it. And then what happens is this is the base peak because it's more abundant. Now, if we delve into it a little bit deeper, when we talk about alpha cleavage in an ether, so that was just heterolytic cleavage of the carbon-oxygen bonds. Now, if we talk about alpha cleavage in the ethers, we end up getting this species here. So what happens is the single electron hops in, and then the one electron here hops in, and then we cleave this piece off. And so that would give us a mass charge of 87. And then alternately, we can have this electron hop in and one of these hop in and then the other one hop up, so we end up with the methyl group leaving. Up here, the ethyl group left. And so we end up with the mass charge of 101, that's what's left. And then lastly, we can have this one cleave off here. And so we end up with that single electron moving in, one of these moving in, and that moving up. We get a different methyl group here, and then this 101 peak as well. And so if we go back to the spectra, the alpha cleavage is what gives us this 87 and this 101. So we can also have alpha cleavage of an alcohol. And so if we start with 2-hexanol, we can break off this. So in the top, we broke off this, and in the bottom, we broke off this. So the mass to charge of the full ion, the molecular ion, is 102. And then we have this species, which doesn't have the positive charge, but what's left is the 45, and that's the base peak. That's the most abundant, so that's the most stable. And then we have the other, which is 87, which is shown here. The other thing that can happen with an alcohol, and it's something that you should always be looking for when you have an alcohol, is the loss of water. So 102 minus 18 is 84. So that's minus 18, H2. H2O. Now, understanding a little bit how H2O leaves, that's going to be the gamma carbon. So we have the OH on the alpha carbon, there's beta, and then there's the gamma. And so the reaction is that the hydrogen hops over with the water that leaves, and then the radicals put back on this species, which is going to be 84, which is 18 mass units smaller than the molecular ion, and that is loss of water, a true signature of alcohols in mass spec. Alpha cleavage in a ketone. So what that means is that we break this bond right here and this bond right here, and so we end up with mass. The molecular ion is 86. Then we have massive charge fragment of 43 and a massive charge fragment of 71. Loss of a hydrogen from the gamma carbon, and we end up with the McLafferty rearrangement. And so is all that tells you is that we end up losing 12, 12, 4, 28. So we end up losing 28 with this species right here. And that's because the carbonyl oxygen forms a bond with the gamma carbon hydrogen, so the gamma hydrogen. And that's just something to be aware of. Mass spectrometry, so the common fragmentation behavior of alkyl halides, ethers, alcohols, and ketones. The bond between a carbon and a more electronegative atom breaks heterolytically, meaning that both electrons go with an electronegative atom. A bond between a carbon and an atom of similar electronegativity breaks homolytically, meaning that one electron goes in each direction. The bonds most likely to break are the weakest bonds that lead to the formation of the most stable cation fragment. So if this seems a little overwhelming or bizarre or difficult because you just jumped back in, that's okay. One of the first weeks in Organic Chemistry 2 Laboratory, you're going to be working on the mass spec worksheet. If you wanted to go ahead and get started on that, you could. I tried to pick homework problems that weren't impossible, so please give them a try. By Wednesday, I'll be asking people to put stuff on the board. You know how it is in organic. We got to push because we got to get all this material in. Anyway, so on the syllabus is the homework for the chapter 14. It's not a huge number of problems because it's just a part of the chapter. So it's a nice way to break into organic. I will see you all on Wednesday in recitation, and remember the recitations. Section 31 starts at 8:30. Section 32 starts at 9:30, not 9:20. And section 33 starts at 12:10. Keep warm, stay safe, and I'll see you on Wednesday. Bye-bye.